Welcome to computer graphics using Autodesk Maya and the Unity engine. It's really just meant to give you a taste of what computer graphics is all about. In following videos, we're going to dive into computer graphics by jumping into Autodesk Maya, taking a look at how models are made, how they're generated, and other such things. And we're going to dive into using the Unity engine to familiarize ourselves with many of these topics. I always like to show this slide. Even though this course isn't specifically or strictly VR, VR is a part of computer graphics. Here is the sort of the old mindset for VR. This is kind of what was popular when I was a kid growing up. These are all ridiculous. And that was one of the biggest problems with VR for a very long time, and it still is a big problem. I mean, just look at this quote from Edward Castronova. Bulky vision goggles that go over your head, the web of wires and straps for your arms and legs, the funny half-chair, half-bike apparatus that you are wiggling around on, the six-sided surround sound rooms at Disneyland that make you feel like you're standing in the Amazon jungle or on the moon. The intent behind these systems are to replace your sense of vision. Many people would consider virtual reality to be here already in our homes, but not terribly immersive, or at least not in the way we like to think of things as being immersive. And by immersive, I mean realistic, right? Plenty of people can sit down on their computers and play video games that are cel-shaded, but they still feel immersed. They feel like they're part of that reality. And for a lot of VR, it's all about immersion, navigation, and interaction. Here's another quote from Edward Castronova. A person can become immersed either way. Either the sensory inputs are so good that you actually think the crafted environment you're in is genuine, or you become so involved mentally and emotionally in the synthetic world that you stop paying attention to the fact that it is only synthetic. And these are a lot of different projects I've been working on while I've been here. Everything from unmanned aerial vehicles to simulating flooding in Camden and Vineland in New Jersey. Here's an educational game I made for kindergarten first graders where you interact with a caterpillar. We actually had Michio Kaku come out and film a segment for Sci-Fi Science on holodecks with us. Of course, down here, something a little bit more silly, but we had some dancing students come in and they created their own dance troupe basically by attaching infrared markers to a dancer, and as he danced around, the guys in the background danced as well. My master's thesis work from a long time ago was for NASA with rocket engine test stands and visualizing data and information. I did a really quick augmented reality project where I could replicate the position of dominoes for a potential project with the museum. Didn't quite pan out. And of course, there's the medical volume renderer I wrote over here, and you can see a much larger picture over here on our 10-sided cave. You can do simulation analysis of weather impact or weather events. You can do resiliency planning. You can take a look at future buildings you may have, or even potentially offshore sites and what impact they'll have on regions. All I'm trying to say is, if you learn this stuff, there is a place for you to use it. Okay, this is woefully inadequate, and computers are so much more complicated than this, but fundamentally, this is truly what a computer is all about, and we have to use computers for what we're doing here. And actually, 90% of the battle, I would say, with learning computer graphics and this stuff is understanding what the computer can take in, how the computer does what it does, and then learning to communicate with it properly. So of course, we've got input devices. We have mice and keyboards or tablets. If you're talking about augmented reality or virtual reality, you might have a video stream. You might have sensors on your head that tell you position or orientation. You may have different kinds of input devices like controllers, like PlayStation 4, or Xbox, or Wii U, and all the different kinds that are out there. It's just us querying information from the world and making it so it's interactive. That, of course, goes to our processor or processors or cores or whatever you want to call it in this case. We've got onboard memory on the processor. We've got other memory as well to hold all other kinds of information. You're going to have your application, which is running. Then, of course, there's typically this sort of barrier we like to think about between the processor and the GPU, although with time that has become less and less of a problem. But we still usually consider the processor or CPU side of things, and then of course the GPU side of things being separate. And a lot of times we have to take care in optimizing things to make sure this barrier doesn't get in the way. But of course, we have your graphics processor, your GPU, your frame buffer. Literally, the screen you're looking at right now, the memory that's storing that pixel information, and then finally your display device, which is probably a monitor or a cell phone or a tablet or a head-mounted display or a 10-sided cave system. It could be just about anything, it doesn't matter. But these are the basic building blocks you need to become familiar with. Almost all computer graphics outputs pixel information. That in this process is called rasterization, all right? Now, picture elements, which is what pixel actually stands for in case you never knew that, store themselves in memory in what's referred to as the frame buffer, okay? This is what continually gets updated and then pushed to your screens. And of course, we have resolution, which is the number of pixels you have on your screen. Of course, that's usually the width times the height. And next up, we have the depth. This is the number of bits for each pixel. The more bits you have, the more colors you can store, the more stuff you can store, the more information you can convey. Now, today, we've typically decided that 24 bits is where it's at, right? So that is values of 0 to 255 for the red, the green, and the blue. When you got 24 bits, you can store 16 plus million colors, okay? Now, a lot of times, almost all the time really, there's also an extra 8 bits, and that's for the 32-bit representation, which is usually for having RGB and alpha, or that is transparency information. So you get 256 levels of transparency from 0 being perfectly transparent, you can't see anything, all the way to 255, which is completely opaque. We are going to create a 3D world with 3D points all over the place. How do you display that on a flat 2D monitor? What is going on here? What is the, hint, hint, pipeline for taking this 3D data and making it look 3D on a flat 2D monitor? I've kind of spoiled this a little bit, but primitives. These are the basic primitive types. Actually, it's a little wrong. Today, we don't use some of these. We'll see that in a second. But the idea is that for a computer to work with our world, our 3D environment, everything gets expressed as points. XYZ vectors, points everywhere, all right? And with points, you can then define lines. And then if you want to conserve memory, instead of specifying lines, line 1 to line 2, that is point 1 to point 2 makes a line, point 2 to point 3. What if you could just specify a line strip? Like point 1 leads to point 2, which leads to point 3, or a line loop. So you don't have to rewrite the fact that V4, vertex 4, is connected to V0. What if it just closed itself automatically to conserve memory? Well, then we got a line loop. All right, what about defining shaded areas or areas that are enclosed? Polygons, typically convex polygons. Typically today, we deal only with triangles. If you are dealing with quads, like in Maya or other programs, usually they're going to get cut in half anyway into triangles. And like in Unreal, I believe the old Unreal editor would take in your models and try to convert everything over to triangle strips to conserve on memory. Just realize if you do see these other things, they're probably just being converted into triangles. For instance, in Maya, if you try to make an n-sided polygon, Maya internally is going to cut that thing up for you. You're just not going to notice until you export the thing. As I've said, everything, and I mean everything, is composed of points. Hundreds of thousands, if not millions of points to make up an object. Here's a caterpillar I modeled for one of our projects, and you can see it's nothing but points. But okay, everything's made out of points. Maybe we should start asking some questions. Maybe we should think about what that means. Do we have to place every point of every object? If I'm drawing an object in a scene, do I have to literally, put them all down? Do I have to do every object separately? Like over here we have a game we made at the VR Center called the Virtual Green School, where it's kind of like The Sims, but with furniture, and not as cool or interesting as I'm making it out to seem. But the idea is we've got all these tables where you're setting up your classroom, several thousand points, and it's the same thing over and over again. And am I really rendering 1, 2, 3, 4, 5, 6, 7, 8, 9? Do I have to specify 9 times the number of points in that object on the screen? What about if I wanted to animate them? They're points. Do I have to tell every single point how to move? What about if I want to copy something? It seems kind of wasteful to duplicate those points. Is there some way to make this easier? Can I just use those points over and over again? Do they have to be separate? What about if I want to scale this thing or rotate it? All great questions, and the good news is they've all been solved. Otherwise, we wouldn't have the games we play. We're going to use this Zergling as an example because I used to like StarCraft, not StarCraft 2 so much, but this is a nice 3D model that we can use. So the first thing you need to understand is that typically we create our models that it's convenient for the modeler or the programmer. All right, you create your 3D model in a program centered at the origin, usually the feet down at the bottom, so that when you move the object around, you're moving it around the feet, although you can always do offsets and all kinds of stuff. But the idea is that also your models are always looking down the z-axis. So z-axis is our forward vector, is what we're going to call here. This coordinate system revolving around the center of that model is called its local coordinate system, model coordinate system, or object space coordinate system. You will hear all three of those depending upon the literature you're reading. So just become familiar with a local or model for the most part. Now, every object has its own local coordinate space, okay? You can think, if you've got all these Zerglings rushing this Ultralisk, for some reason, even though they're on the same team, it looks like. I don't know why they're doing that, but they are. Each of them have their own forward vector, or orientation, their own position, their own location, okay? Typically, we share vertex data. That is, there's one Zergling, all right, with all the vertex information, all the point information, but each one of them have their own unique transforms, okay? We call each one of these Zerglings an instance. It has a unique position, rotation, and scale, but it shares the same vertex data. And you will see this in Unity. That's what your transform is. That's what, when you create a game object, that first little thing on the top that says transform is holding your translate, your rotate, and your scale information, okay? And that's unique per object. However, the mesh, the vertices are not unique. Now that's the local coordinate system. We then need to bring all these guys into the same world, and that's called the world coordinate system, a common reference system where we begin positioning things relative to one another, okay? The world has an origin, and these things exist within that world. Now in computer graphics, if you get deep into it, you look at the books and so forth, you're going to find out that there's a lot of different kind of transforms. But the reality is there's pretty much only three that you need to care about, and that's translation, rotation, and scaling. The reason why these three are so prominent in Maya and in Unity and every other engine out there is because this does nearly everything you need it to do. Math time. Not really. This is an introduction. We'll cover the math in a later video. We're just trying to get you familiar with all these things at the moment. So first off, utilize linear algebra. Yes, linear algebra. Do not dread it. It is your savior. I personally hated math when I was in college, and then I got into this stuff and realized I needed to actually remember everything about it. But we use linear algebra, matrices, and these matrices are incredible. They're able to store all of this information in a tight, convenient format that a computer is going to be able to logically work with, okay? We're going to have translation, which is this matrix right here with the identity down the middle. Basically, that does nothing. And then we have our translate X, translate Y, and translate Z. Of course, rotation as well. We have three different rotation matrices in this case, using Euler angles, basically, and uses sine and cosine to figure out how to rotate an object. And you need to do this for each axis, X, Y, and Z. Then, of course, there's scale. SX, SY, SZ, and 1. This matrix right here, it's that diagonal you see on the translate part of it, okay? The next part is, so you have your local space, you've got your world space, now you need to put it in reference to the camera, right? Because you, when you're playing a game or you're looking at something in an application, you're looking from a location. You have a camera that you're moving around. You need to draw everything in that world with respect to that camera. So we put the camera at the origin, and then we actually rotate and transform everything based upon where that camera is. So here's a camera right here, a camera position, and here's all the world elements. You'll notice that the camera is moved back to the origin, and then it's rotated to look down the z-axis, or actually in this case, the negative z-axis for this. And you can see that all the other elements in the world have also been moved to compensate. And that's always something I love about computer graphics. It's like the exact opposite of how you would do something. In this case, you move the world to fit the camera. You don't move the camera to fit the world. And here's, of course, a view of a camera in its frustum, which is this sort of pyramid-shaped object you see right here. It has a near clip plane and a far clip plane, which is the near is the closest one, the far is the further one out. Only elements within those two regions are going to be rendered. Stereoscopic systems have a little bit harder time, and this is why they usually have higher requirements. Instead of rendering one image, we're actually rendering two images, okay? That means we have half the time to update things. We're rendering a left eye and a right eye of the world, and each one has just a little bit of variance between the two, especially if an object is close to you, all right? And it's that difference between those buffers that gives you the sensation of 3D. So we're not going to go into these now, but I just wanted to kind of show you the full transformation pipeline. model space, where you model that object, where it's locally stored. World space, where all objects have some location with respect to one another. Then, of course, world space turns into camera space. But then you have to do things like computing the lighting, which is how things are illuminated. You have to project this onto an image. You have to clip things that shouldn't be there, and you have to map it to your screen, okay? It's a complicated process. But the good news is that engines like Unity handle all of this for you, so you don't have to do all this nonsense yourself. We've defined the shape of an object. That is the vertices that make that object up. But we also need to describe the visual properties of that object. We need to give it color. We need to tell it how it interacts with light. We do this through materials, okay? So you're gonna have materials in Maya and you're gonna have materials in Unity. And the material describes the visual properties of the mesh. It's kind of like a container. It holds the shader, which is code on your GPU that's basically going to say how to handle the points and the pixels. It holds references to things like images. It will have input parameters such as how shiny something should be or what color maybe you want to tint things to be. It's responsible for how things are visualized, and you have to have a material. If you don't have a material on an object in Unity, it's going to turn this funky purple color. The important thing to understand is that we can use 2D images to colorize models, all right? And this is the process of UV unwrapping as well as texturing. And this is where we jump into programs like GIMP Shop or Photoshop to do this, okay? This is where we go from kind of 3D to 2D. Although nowadays, we can use a lot of programs to paint directly onto these 3D objects. But to do that, we need to take our 3D object, cut it apart, and flatten it down to 2D space, all right? And this is never clean. It is not possible to do this without distorting your mesh. So on the right-hand side, we see our caterpillar all cut up with seams. And on the left-hand side, we see the unwrap UVW editor where we're seeing how I place these, as well as the texture I made inside of Photoshop to do this. Another thing that's really important about materials is they have shaders. This is a shader I wrote a while back in WorldViz Wizard that was to replicate the Bioshock shader effect you saw in Bioshock Infinite. The idea was you could bring in any asset like this sphere with a brick background, and by applying this shader to the material, it would then immediately replicate the Bioshock Infinite effect, right? So it went grayscale, it's got noise through it, and it also generated that sort of weird squiggle effect on the border, which was kind of a pain in the rear. It required quite a bit of math to generate something that's all squiggly like that, all right? But that's it. I mean, this is incredibly powerful. All I had to do was put a new piece of code on this object, and all of a sudden now it has a completely different visual feel and effect. Lighting. Ooh, lighting is a huge topic, and it's lately has become incredibly important with computer graphics. It's no longer about how many polys you can push, it's about how accurately can you replicate lighting. The most realistic scenes we see nowadays are those that are properly rendering a scene, that is properly replicating how light bounces around a scene and interacts with objects. Now we have two different models. The past, we used local illumination models. This means we simulate that light is bouncing off an object. Basically, we put a light in the scene, and then we look at the surface of an object, and we don't care about anything else in the scene, just that surface, okay? And then we figure out how the light interacts with it. But that's not a good idea if you think about it. How are you going to replicate shadows? Shadows are about objects being in front of one another. There being a relationship spatially where objects are. Local ignores all of that, but it's incredibly fast. And local is still used today, and it can look pretty good if you're careful. But global illumination is really where it's all at. This is actually where you calculate how light is moving around the scene. You may bake this in Unity beforehand. It can take a while, it's complicated, but it's basically simulating light bouncing off surfaces and interacting with the environment before it gets to the camera. So we have the ambient component. The ambient component is sort of a cheat. It's just a way of making everything a little bit brighter, all of your dark spots brighter, okay? Usually this is set to like 0.1 for a lot of scenes automatically. I believe it is inside of Unity as well. You have to go into the lighting properties to change this. Then there's the diffuse component, which has to do with the angle of the surface in relation to the location of the light. And of course, finally, there's specular, which has not only to do with where the light is, it also has to do with where the viewer is. This is the pipeline that we typically use. We have the tool stage, which is going to be Autodesk Maya or Max or Houdini or all the different things we create content with. We have the asset conditioning stage, because rarely secondarily, when we build stuff, is it in the correct format? And then we have the application stage, which for us is going to be Unity. And then we have the geometry processing stage and the rasterization stage, which is what happens when you're actually rendering, when your game is running, okay? You're pushing out geometry, it's calculating where that geometry is, and then it's drawing pixels to your screen in the rasterization stage. Now, what you need to understand is that rendering is all about a pipeline, okay? It is cut up into different segments, and the idea is that by doing this, you can achieve work faster. But there's a huge limit to pipelines, and that is you can encounter a bottleneck. If one guy on the assembly line decides to be slow, everyone after him has to sit and wait. And that's why your games can stall, and that's why you get a poor frame rate. If something about that scene is causing things to slow down, everyone after that is going to slow down, and then everyone's going to suffer. So in our tool stage, I'd already mentioned this a little bit before, but you're going to create your meshes, your textures, your animations, a lot of your content really, your sounds, everything else, in external programs such as 3D Studio Max, Maya, Blender, Houdini, Lightwave, XSI, and the list keeps going on. SketchUp even, and so forth and so on. Or, if you're really clever, and we'll be talking about this in some other videos, you can create them directly through code itself. Now, these tools are going to assist you in modeling, lighting, animation, texturing, rendering. The idea is that they make your life easier, and a lot of times they make it so you don't need to understand the math or the complicated programming that's going into these things. You can just do them with little care. Although I will say right now, the more you understand and the more you know about how these things work, the more powerful you are going to be. And then, of course, you have the last three stages. The application stage, which is going to be Unity in our case. It's going to handle our scripts. It's going to do collision detection for us automatically. It's going to handle animations and physics and sound and all kinds of wonderful things. We then have the geometry stage. That's where we are going to transform all those local coordinate vertices to their final location and figure out where these objects should be on the screen. And the last step is taking all this three-dimensional content and determining where to draw our pixels. To get a little understanding of why this works the way it does, I'd like to talk a little bit about the history of the GPU. Now, for me especially, this is my history really, because I was a high school student when all this stuff started to happen. I was into games, and I needed to know this stuff so I could get the best performance out of my computer. For a while there, graphics cards existed, but they were not for consumers at all. If you're at home playing games like Wolfenstein 3D or Doom, everything was being processed on the CPU. The great news was the programmers could do whatever they wanted. They had tremendous freedom. However, it required the programmer know a hell of a lot more because you were responsible for making everything actually work. The bad side was you had limited computational power. Now, Descent in 1995 came out, and this is touted as the first true 3D game. And of course, Quake 1 soon came out after that. Now, with Quake 2, as well as Unreal 1, we needed something more, okay? We need hardware acceleration. You had to have a fixed functionality pipeline at the time. The idea is they made it fixed, which limited the developer, but at the same time gave them a lot of power, gave them the ability to use something else other than the CPU to do work. It freed them, but it also restricted them. In 2004, we had a big break. We finally got away from the fixed functionality pipeline. We got into the programmable pipeline. And the idea behind this was to once again give freedom to the artists. Well, I say artists, but the reality of the situation is you had to be an assembly programmer for the first kind of shaders that came out. So there really wasn't a whole lot of freedom unless you had a hell of a good engineer on your team. But this started it. This started the trend for us to be able to program our own effects on the GPU. And it's where we're at still today. So I love this slide because it really shows the transition of quality. We go from Unreal Engine 1, which I'm incredibly fond of. I played this game incessantly at home in high school. We've got the Unreal Engine 2, and it's a notable jump, right? I mean, the texture quality is higher, so obviously, things got faster. We had more processing power. We had more memory to work with, but it still is very much in the same line, right? It still looks very similar, just a little better. Then we come to step 3. You can now start programming your own effects. And remember, in the world of computer graphics, a lot of times we don't care if it's right. We just care that it looks good. You are able to do things that faked it to look better than it really is. So for instance, in the case of this gentleman over here, his poly count isn't tremendously higher, but we're using things like normal mapping and specular mapping to make the eye believe he looks better than he does. He's also got this nice glow effect kind of around his body, which is probably a post-processing shader acting on all the pixels after the scene has been rendered. You get to do more. You get to have artistic freedom to try out new techniques and fake different kinds of effects. Now, there are many more shaders out there than in the past. For instance, vertex shaders and fragment shaders or pixel shaders were the big two in the past. But more recently, we have tessellation shaders, we have geometry shaders, and even compute shaders for just doing some hard math. And of course, with vertex shaders, you can do some pretty amazing things. These are all images of the same teapot. However, the vertex shader has manipulated the underlying geometry to produce these different results, such as skewing it or distorting it and providing different kinds of color based upon the amount of distortion. And of course, if you think that was neat, the fragment shader or pixel shader can do even more. And the pixel shader is really responsible for that final outcome, that final look and feel. Everything from cell shaded to wireframe to drastically changing the feel or the texture of an object. You can pretty much do anything you want to in a pixel shader, and if you can't do it in one pass, you can always do multiple passes to create different effects. Now, I just wanted to briefly discuss other topics that we're going to come across inside of our trip into computer graphics. First, of course, is animation. This was a T-Rex I made a long time ago. But the idea behind this is that you have a Tyrannosaur composed of hundreds of thousands of points. And of course, you need to be able to manipulate those points. And remember how earlier I talked about how vertices are nothing but lots of points, and the last thing you probably want to do is animate lots of points. Well, you put bones in there, and you rig them up to react in a certain way, and you move the bones. So instead of moving, a couple hundred vertices, you move a piece of the spine, or an arm, or a leg, and it reacts in the way you expect it to, because you've taken the time to program it that way. And of course, there's always AI. This is an incredibly simple example, but one I always love to show of basically a flee and a seek algorithm. We have the green guy constantly trying to target the yellow one, okay? And that randomly changes as time goes on. And you have everyone else constantly fleeing away. You can see all the vectors being calculated for the flees always away from the green guy, and you can see the green guy's vector is always trying to get to that other person. Now that's a huge sort of high up level look at computer graphics. We looked at a lot of different concepts, and the entire idea behind this whole video was just to familiarize you with a lot of different terminology and some of the different things we'll be exploring using Autodesk Maya as well as the Unity engine in the future. Thank you very much. Remember to like or subscribe if you enjoyed this series. Thank you. Bye.